Hey everybody, Dr. Nelson here. This is a video lesson about something called scaling an area. All right. So before we talk about scaling an area, let's get warmed up by trying this problem right here. All right. It says true or false. Okay. The second shape is a scale copy of the first. All right. So here's the second shape over here. And the question is that a scale copy, okay, of the first? Now, in order to do that, we have to figure out the scale factor of all the sides, right? So we have to first look at the corresponding sides, all right, and then see the ratio of the corresponding sides to get the scale factor, okay? So let's look at this one here. Here we have a 3, and notice the corresponding side over here is 9, right? And remember, we always take the new length and divide it by the original to get the scale factor, right? So when I do 9 divided by 3, I get 3. So that means the scale factor has to be 3 for all the other corresponding sides for it to be a scale copy. All right, so let's test this. Here we go. So here we have 15 and 5. Well, I know 15 divided by 5 is also 3, right? So that works. Here we have 3.3, and the corresponding side over here is 1.1. So 3.3 divided by 1.1 is also 3, okay? But look at this one. Here we have 4. And the corresponding side over here is 2. So when we do 4 divided by 2, we get 2. All right, so because 2 is a different number than 3, okay, that means the answer to this question is false. All right, the second shape is not a scale copy of the first. All right, so today you're going to investigate what happens to the area of a shape, okay, when it's scaled. So really the question is, what happens to the area of a shape when the dimensions are changed, right, by a common factor? All right. So here's the scenario. All right, Jack has a lawn mowing business, okay? One of his clients pays him $20 to cut a 100-foot by 50-foot piece of property. Okay, so the property is a rectangle, okay? And he gets $20 to cut a 100-foot by 50-foot piece of property. Jack has been offered, okay, $40 to cut a 200-foot by 100-foot piece of property, okay? So is this a good or bad deal for Jack, okay? So notice that the money doubles, right? So when we go from 20 to 40, the money is times 2. And look at the dimensions, okay? When we go from 100 feet to 200 feet, that also doubles. And when we go from 50 feet to 100 feet, that also doubles. So the question is that a good deal for Jack? All right. So take a look at this. This will help you figure it out. It says, what do you think is going to happen to the area of this shape if both the length and width are doubled? Okay. So here's the original shape that Jack got paid $20 for. Let me put a big 20 right here. Okay. So the question is, what's going to happen when these dimensions change from 50 to 100, right? And from 100 to 200. All right, let's figure this out. So I'm going to double this distance. So I'm going to go 50 down to 100. So I'm going to double this way, okay? And then I'm going to go from 100, which is here, to 200, which is way over here, right? So I'm going to go over twice the length. So there's 100. And now 200 is going to be double that, right? Right about there. I'm going to go all the way back up to 100 and all the way over like this. So take a look what happened. When we doubled the dimensions, the area actually quadrupled. Now we have 1, 2, 3, and 4 times the length, right? So in order for Jack to be paid right, okay, he would have to get 4 times the amount of money, all right? If we go back to the problem, right, he was only being offered twice the amount of money. So is this a good or bad deal for Jack? It is a really bad deal for Jack, because when the dimensions double, okay, the amount of area increases 4 times.